Bismillahirrahmanirrahim. Assalamu alaikum students. So today we are going to start chapter number 6, which is system design, decomposing the system. So outline of today's lecture is introduction, then overview of system design, then system design concepts. In system design concepts we discuss subsystems and classes, services and subsystem interfaces, coupling and cohesion, and layers and partitions. So the design of a floor plan while making an architecture of a house is similar to system design in software engineering. So the table given maps the architecture and software engineering concepts to give you a better understanding of it. So components in architecture concept is called room, and in software engineering concept component is called subsystem. Interface is called service, and in architecture concept it is called door. So in the same way, non-functional requirement like living area, and here is response time, and functional requirement that it should be a residential house having the characteristic of a house, and in software engineering concept it is called use cases. And costly rework, moving walls, and change of subsystem interfaces. If the interfaces change, then it will be a costly rework. So overview of system design. System design results in following products: design goals, which describe the qualities of the system that developers should optimize. The design goals are derived from non-functional requirements. Then software architecture, it basically describes the subsystem decomposition in terms of subsystem responsibilities and dependencies among subsystems mapping to hardware, etc. Then boundary use cases, it describes the issues in startup, shutdown, and exceptional handling. So overview of system design, like analysis we discussed before, that what are the products or outcome of analysis phase is a set of non-functional requirements and constraints, is dynamic model, which consists of sequence diagram and state diagram, is analysis object model, which describes the entities manipulated by the system. Now in system design the system design has the following outcomes or products, which are design goals, which are basically derived from non-functional requirements, and then subsystem decomposition, the dependencies among subsystems, and the responsibilities of subsystems. So these are basically the outcome of system design. So the activities of system design represented by UML activity diagram. So let's discuss system design concepts. The first is subsystem and classes. So to reduce the complexity of the solution domain, we basically decompose a system into simpler parts. Fine. What is subsystem? Is a replaceable part of the system with well-defined interfaces. How you can interact with the subsystem? With well-defined interface that encapsulates the state and behavior of its contained classes. So what I said you before, to reduce complexity of the system, we decompose a system into simpler parts which are called subsystems. So a subsystem corresponds to the amount of work that a single developer or a single development team can handle. So, by decomposing a system into independent subsystems, concurrent teams can work on individual subsystems, and in this way, the the development can be done fastly. So, concurrent teams can work on individual subsystems. So, so subsystems and classes. So, a subsystem is made of a number of solution domain classes. So, a system has many parts, and class is a part, and subsystem is a part of it. And if a subsystem is complex, we recursively apply this principle and decompose a subsystem into simpler subsystems. Means a subsystem has many parts in it, which can further be divided into subsystems. So, subsystem decomposition or for accident management system, which we discussed previously also. Subsystems are shown as UML components, as this notation is for component, and dashed arrows indicate dependencies among subsystems. So the dispatcher interface which is a user interface for the dispatcher, and a field officer interface subsystem, which is the user interface for the field officer. These two are subsystems. Incident management subsystem that creates, manage and store incidents. Resource management subsystem, map management subsystem, and notification subsystems. So these all can be subsystems in accident management system. So various programming languages have provided constructs for modeling subsystems. Like Java has provided package construct to model subsystems. You can place all the relevant classes of a subsystem inside one package. So what is service? A service is a set of related operations that share a common purpose. So the set of operations of a subsystem that are available to other subsystems form the subsystem interface. So interface is what? Basically a set of operations that a subsystem offers. So what is you are already familiar with interface concept in OOP. So subsystem interface is what? Is a set of operations that a subsystem offers. So the subsystem interface includes the name of the operation, like what are the name of the operations, like create, edit, what are the operations, what parameters it takes, what are the types of the parameters, whether int, float, whatever the types, and what is the return type. So this is an example of a subsystem which we seen in the previous slide, notification subsystem. What services the notification subsystem offers? It can offer lookup notification channel service, it can subscribe to a channel or unsubscribe from a channel, it can send notice. So these are the services that this subsystem is providing. So in the same way, a subsystem can provide various services to other subsystems. So now in good design, the subsystem interface object describes all the services of a subsystem interface. So there are two kinds of interfaces like we have discussed in component diagram lecture. One is provided interface and other is required interface. The provided interface is shown with a ball icon and the required interface is shown with a socket icon. Fine. So what this diagram shows, so services provided by resource management subsystem. So these are the services provided by resource management subsystem, uh, depicted by UML component diagram with ball and socket notation depicting provided and required interface. So what this diagram shows, that resource management provides resource update service interface and resource allocation service interface, and these two subsystems require these interfaces to complete its operations. So in other words, field officer interface requires resource update service interface that is provided by resource management subsystem. So in this way, through subsystem interfaces, the subsystems interact with one another. Next concept is coupling. So this is an example of incident management subsystem that we are discussing. So the alternate one is that all subsystems which is map management subsystem, resource management subsystem and incident management subsystem access the database directly. So what is the disadvantage of it? Making vulnerable to changes in the interface of the database subsystem. What it means, that if any change occurs in the way the data is stored, if any change occurs, for example, database vendor is changed, or if any change occurs in the database storage mechanism, will require change in the subsystems, in the three subsystems also. So the alternate two shields the database with an additional subsystem, which is storage. Only one subsystem will need to change if there are changes in the interface of the database subsystem. If some database storage mechanism is changed, only one system needs to be changed, as we have placed an intermediate system to separate the database from these subsystems. So now the change in the database subsystem will not affect the three subsystems, but only one storage subsystem, as this is interacting with the database. So what design is better in terms of coupling, alternate 1 or alternate 2? obviously alternate too. Next concept is coherence. So coherence means dependency among classes in subsystems. There should be tight coupling among classes in a subsystem. High coherence means the classes in the subsystem perform similar tasks and related to each other via many associations. And low coherence means lots of unnecessary classes and with no associations among them. So, uh, decision tracking system represented by UML component diagram. So the decision subsystem has a low cohesion. Why it has low cohesion? Because as you can see, the criterion, option and design problem class have no relationship with these three classes. So in cohesion, the classes within one subsystem has are tightly associated with each other. So what we do, we decompose the decision subsystem into two subsystems. So one is the rational subsystem containing these classes, and other is planning subsystem containing these classes. So alternate subsystem decomposition for the decision tracking system. Now the subsystems interact with one another through interfaces. So what this indicates, that the rational subsystem provides an interface which is required by planning subsystem. So in other words, the planning subsystem requires services of rational subsystem. So by making subsystem highly cohesive, it enables the reuse of subsystems. You can reuse each subsystem independently. A good design should have high cohesion, means the classes in the subsystem perform similar tasks and related to each other via associations, and have low coupling, means the dependency among the subsystems should be minimum. But in general, there is a trade off between cohesion and coupling, because when you try to increase cohesion, like we have done in the previous slide, we try to increase cohesion by decomposing a system into two subsystems, but this increased coupling also, because now in order to communicate the subsystems, interfaces are also increased. That's why coupling will also increase. So you have to do trade off between cohesion and coupling. So next is layers and partitions. So a hierarchical decomposition of a system yields an ordered set of layers. So a layer is a grouping of subsystems that are providing related services, but with following restrictions. A layer only depends on services from the lower layer. So a layer depends on services from the lower layers in the hierarchy, and a layer has no knowledge of higher layers. Fine. So as layered systems are hierarchical, so this is a desirable design because hierarchy reduces complexity of the system. So this example shows the hierarchical decomposition of a system. So subsystem decomposition of a system into three layers: layer 1 top, layer 2 mid, and layer 3 bottom. So the layer that does not depend on any other layer is called the bottom layer, and the layer that is not used by any other is called the top layer. So this is an example. So a subset from a layered decomposition that includes at least one subsystem from each layer. So one subsystem from this layer, from this, and from this is called a vertical slice, like A, B, and E. One subsystem from each layer. This is called a vertical slice. Whereas if we take DG only, we don't take A in that, this is not a vertical slice. So this is an example of close architecture of OSI model. You are already familiar with the 7 layers of OSI model, which is physical, data link, network, while each layer is responsible for performing a well-defined functions. So in addition, each layer provides its services by using services of the layer below as indicated by the arrow. So close architecture means that a layer is using service of a layer immediately below it. And another architecture is open architecture, which indicates that a layer can use service of a layer immediately below it as well as the deeper layers. Like if the transport layer is using the service of network layer as well as data link and physical layer. So this is an example of closed architecture OSI model. The OSI model decomposes network services into 7 layers, each responsible for different level of abstraction, as I told you before. So partitioning. So partitioning is the dividing a system into independent peer subsystems which provide services to each other on same level of abstraction. Like on same level, the subsystems in a partition provide services to each other. So such that A calls services in B and B calls services in A. These are peer to peer. So partitioning is basically dividing a subsystem into independent peer to peer subsystems which provide services to each other at same level of abstraction. So by applying partitioning and layering, you can decompose your system, but apply partitioning and layering with care, as excessive partitioning or layering can increase complexity of the system instead of decreasing. Thank you.